final completion of Einstein's theory of relativity this November. So there's the beginning part. Here are some practical definitions of time. I was, for my position at the Naval Observatory, once you get this job, they think you know everything. I got called and asked to say what time was, and I gave this definition. That coordinate which can be most simply related to the evolution of closed systems. You can still find it in Britannica online. So this is a practical definition. It's a coordinate that helps you explain what's happening. That's sort of like defining a symphony by the notes in it. It's missing something. And a lot of people think, we'll go over some more definitions. I don't think Yogi Berra really did this, but it's been ascribed to him. Time is nature's way of making sure everything doesn't happen at once. And space analogy. This actually has validity to it. And so one of the questions that people have is, when did time start? I think we know what time is. Did it just start now? Maybe, well, we just began now, and everything from dinosaur bones to bad grades, it's just memory that we were created with. That could be. A lot of people say maybe it started at the Big Bang. That's a singularity. I'm not going to talk about it, but I'm sure you all have heard of the Big Bang. Or maybe it went infinitely in the past, and the Big Bang was just an event. And some people say, well, in the past there were some multidimensional brains, and they collided, and that collision created the Big Bang and time. But you'll notice if that happened, time is sort of involved in all that as well. What do you mean to say they collided? And when did time stop? Maybe time will never stop. That's how we tend to think of it as we go through life. But others say, no, it will stop when the universe collapses upon itself. That's possible. Or it could stop right now. Or just in a second from now. Or when the brains separate, which will rip the fabric of space and time, that could be going on right now. We wouldn't know it until the rip comes to us. And all of these things can be the subjects of books and conferences and arguments. I'm just telling them now to get them out of the way and set the stage for how we got to where these questions could even be considered. And this is one that I really like. I mean, I like it, but it really intrigued me. Maybe it'll slowly die out. The current theory says the universe will expand indefinitely, in fact, faster and faster. Will be left, after many, many eons, will just be a dilute gas. That's all it'll be. And there'll be little fluctuations back and forth, but there'll be no way to make a clock in such a thing. No way to keep track of time. So what does it mean to say there's a time? There's just this little gas that's going back and forth. Or maybe it's a trick question, because time doesn't even exist. And there are ways that you can say that. Or some people say that maybe time runs backwards. It's a human construct that time goes forward. That's not a question. Not a question. Okay. But let's start with Newton's mechanics, which is how people really tend to look upon it. And he thought that time flowed evenly throughout the universe. And he came up with other rules, like energy and momentum are conserved, and F equals ma. And he sort of set the stage for what we call classical physics. And I would call him the most brilliant scientist I know of. Although everything he said is no longer believed. Or I turn that around. Nothing he said is believed anymore. To be exactly right. And we're going to talk about his theory of time there. And I'll give you something about his law of gravity first. It was indeed inspired when he was sitting underneath a tree trying to escape the plague of London, and he saw an apple fall down. And the mass attracts mass. Heavier bodies pull more. Heavier objects feel more force, but they have more inertia. So heavy and light objects fall at the same time. This contradicted Aristotle, who thought heavy objects fell faster. And he also came up with gravity weakening at the square of the distance. And that was an important thing, and he developed calculus to show that the force that pulled on an apple, if it fell with the square of the distance, would describe the moon in its orbit. That was not a simple thing, because with the moon far away, you could think of the Earth as a little point source and the moon going around. But the apple, right next to the Earth, you can't no longer consider the Earth as a point source, so why would that work out? He showed with calculus that it all works out. And what did he think light was? Well, he thought of little particles, they could spin, and they didn't have to be round, and he had all kinds of things, and they had mass, like particles, and when they hit your eye, you could see, your eye would detect them up. And he had theories that red light was heavier than blue light and it traveled in glass. And this was widely believed at the time. They thought it was great. Although one of his contemporaries, Robert Hooke, you might know of Hooke's law of how springs work, he said, nah, light's a wave, but he wasn't believed. He wasn't as smart as Newton after all. And so this dominated for 2 centuries. Alexander Pope, an Elizabethan poet, said, nature and Newton's laws lay hid in the night. God said, let Newton be, and all was light. But science progressed. And in 1861, Maxwell showed that light was waves. And here's his reasoning, which I think you all know the pieces of. You may not have put it together. Changing electric fields make magnetic fields. You all learned that in grade school. That's how electromagnets work. And then he thought changing magnetic fields make electric fields. That's how generators in the car work. Change electric fields, you make a magnetic field. So changing electric fields and magnetic fields, they can switch back and forth and make a wave that will move forward. And he could do the math, and he came up with a startling fact. The speed of light he got by doing the math through that is correctly predicted by what we know from having measured the speed of light. This is the famous Maxwell's equations. Now I'm going to show them to you. There they are. And these say in mathematical form just this. So, and that was, of course, once for religion, that God just set up all these equations, and then everything else followed. So we're not talking about religion here, we're talking about everything that we don't know. Like the Michelson-Morley experiment came along in 1887. These guys decided, well, if it's a wave, what's it a wave in? It's got to be a wave in something called the ether. So light was believed to be a wave in the ether, and if it's a wave in the ether, then its travel time would depend on how the Earth was moving. So if the Earth was moving with respect to the ether, it would see light as moving slower if it was moving in the direction of it, or it would see light as moving faster. So these guys, Michelson and Morley, tried to figure out how light was moving in absolute space, which Newton also believed in, by setting up this little apparatus, which I won't describe. You can find all this on the internet, though. And what did they find? The speed of light was in the same direction, was the same in all directions, no matter which way they turned their apparatus, all year long. So the Earth was stationary with respect to the ether all year long. But the Earth goes around the sun, or so we were taught. So if it was stationary in June compared to the ether, it should be moving 60 kilometers per second in December. And it wasn't. They could rule that out by the data. So how to explain this was a dominant question of the late 1800s. They had a lot of theories like the ether drag, which means maybe the Earth is carrying the ether with it and making it all work out. But none of them were very convincing until Einstein came along. He tried to imagine what would a light wave look like if you were traveling alongside of it at the speed of light. You'd see all this motion, right? No, you wouldn't, because you're traveling at the speed of light. You don't see these things moving. If they're not moving, you can't have electricity turning into magnetism and back again. There wouldn't be any light. So it would look stationary, and the field would not be changing, the magnetic field would not be changing from the point of view as you're moving along, so you don't have a wave. So how could they be turning into magnetic fields and back again? Yeah, this was a issue, and he came up, the answer brought about the end of Newtonian space and time. It did not last, talking about Newton's laws, the devil howling, "Ho, let Einstein be," and restored the status quo, which is that we don't know what we're doing, what we're talking about. He came up with a special theory of relativity in 1905. He said, well, nothing then can go to the speed of light. That's the rule. If you have a problem going at the speed of light, well, you can't do it. So you won't have that issue anymore. And he also said that all non-accelerating observers are equivalent, so everyone gets the same physics, no matter what speed they're at, as long as they continue going at the same speed. And therefore, no experiment can truly say which observers are truly at rest and which ones are moving. And all observers will measure identical values for the speed of light, which was what Michelson and Morley. Whether you're moving towards the light source or moving away from the light source, are stationary with respect to it.
Give
Thank
it
you
to
very
me.
much.
Zach,
Ah.
don't worry about that.
No, I like that.
Gary.
I stole a passbook when I was a kid like you. Yeah, I'm not a good role model. So nothing to go faster than the speed of light. When I told this to my brother many years ago, he said, well, how about this? You're on a spaceship, it's going at half the speed of light, and you shine a flashlight. Now, the flashlight got a head start. It's on the spaceship. Won't it perceive it's going 1.5 times the speed of light from somebody on Earth? Certainly, if you're on a train and fire a gun, the bullet from that gun will be going faster compared to somebody on Earth than if the train was stationary. Well, why not light? And the answer was no. Well, it doesn't work that way. Einstein, so I said I wasn't going to do many equations, or maybe I didn't say that. He had a law for adding this up, where if you're on traveling one and relative to another, and that was the rule that came out, and there's a reason for that rule. And if you said one of them equal to the speed of light, c, then the final answer is still the speed of light. So that seems like a contradiction. It does not disprove it. It's all relative then. Depending on their velocities, you can observe about what's stationary, how fast time moves, how long length is. He had to bend all of these things to derive that little formula I showed you next, and to explain all this. He had to change our concepts of time and distance. But anybody, meaning a freshman physicist, can compute what an observer A will measure given these data. So even though people will disagree, the laws are still there. You can convert from one to another with the theory of relativity. And just to show you how that works, I'll write down the equations. All of them will agree that nothing travels faster than light. That's the basic thing for which you have to permute everything else. But a stationary observer will think a moving observer's time runs slow. And this is a formula he got for that. So, 1 divided by the square root of the speed of over c squared. V squared over c squared is the dominant thing, and that's the square root. You think the clocks run slow, and you see, that's Salvador Dali. He was inspired by relativity. If they have a yardstick, he thinks that's going to shrink, and you got a formula like this. And it'll be heavier too. The mass is greater. But all observers will agree that energy is conserved. The famous formula E equals mc squared, which is not equal to the rest mass. It's equal to the rest mass. It's equal to the mass after you put in that term. Interestingly enough, here in St. Louis, these same equations were given 1 year before Einstein, in 1904, by Poincaré. I don't know how many of you know Poincaré. He was a great French astronomer and a physicist. But he came here to a meeting and he says, hey, we could explain the Michelson-Morley experiment if we just say things shrink and all that. And he presented these equations and as a curiosity. And that all was to him. But Einstein turned it into a fundamental thing that you get just by playing with the math if you say that you must have the speed of light be a constant. Say that, and all the rest of it follows. You can work it out in a class if you become a freshman and take relativity. And they also came out that a certain combination of space and time intervals is the same. This is important because I'm going to talk about it later. That's the separation in space minus the separation in time with the speed of light in there. You all would agree that just the separation of space here, the same. Everybody would agree that two things about their distance being apart. That's Newtonian rules. You agree about that. And Newtonian rules also said all observers would agree about the time being different. Well, Einstein says they're going to disagree about their space error. They're going to disagree about the time error difference. But if you subtract the two, all observers are going to see that as a constant. He calls that the interval. Is it true? Is it proven? Do things really go slower? Yes. One of the first proofs was with muons. These are elementary particles that decay. They could measure them in cosmic rays. somebody went to a mountaintop in 41. And it was done again much better in 63. I actually studied under him. He was my advisor when I was at MIT, although he hardly was, because we went on strike then in 1970, and then I stopped going to school. That was over the Vietnam War, but that's to the side. So if you look at the decay of the muons, you can get their lifetime and their decay rate. These muons that were in cosmic rays were going at almost the speed of light, 9952c. And what was their lifetime? Well, the inferred lifetime was 2.2 microseconds. But in the laboratory, if they're stationary, it's 1.56. They were taking a lot longer to decay than they should. That's the slowing down predicted by the theory of relativity. And then a little later, at where I work, at the Naval Observatory, these guys flew an atomic clock around the world, and that was always going, and sure enough, they got the same thing predicted by relativity. So they directly proved this by flying an atomic clock around and comparing it to the other clocks that didn't fly. Another thing interesting now is we no longer have the speed of light variable. They've defined the speed of light, so it's exactly this number. And we no longer have a yardstick or a meter in Paris. It used to be a meter was defined by a special bar in Paris that they kept in a safe and took it out every now and then to make measurements against to know how long a meter was. No more. The meter is defined as how far light travels in that much time, because we can measure time with atomic clocks very good, and that's the most accurate way to do it. So what is causality? What makes something cause another? In relativity, if time is no longer such an absolute thing and people can divide it up differently. Well, he said events are indisputable. Indisputable. We assign them numbers, coordinates in space and time under certain rules. So we may take a yardstick and make little marks for surveyors, and we have clocks to assign them. And we do that to the events. But if light had time to travel between these events A and B, if it could go there, then we know which one came first, because one could influence the other. So then we know which one did it. If light did not have time to travel between them, and here's where this number comes in. This actually is the distance minus the time between the events. So if light had time to travel, this will be less than or equal to 0. And then we know that A caused B or B caused A. If light could not go between them, then different observers will disagree about which was first. In the formula, that's when that is greater than 0. So the order of time is inseparable from causality. He stripped time down from an absolute thing to just when something can kick something else. If you can kick it, you're first. So here's an example. Consider two events. You got the Nobel Prize in Stockholm, and according to Wikipedia, that was in 1922. And then event number 2, a supernova exploded in the Large Magellanic Cloud, which is about 400,000 light years away. And we saw it in 1987 on the Earth. So which happened first? Did the supernova explode first, or did Einstein get the Nobel Prize first? Einstein got the Nobel Prize first?
No, the supernova.
The supernova came first because it took 400,000 years to get here. You were right, and all the other questions in the other classes. But now, you are wrong, depending on who you are. Oops, this has jumped ahead. You can't say which happened first, because this one could not have influenced that one. The light didn't get here until 60 years after Einstein got his prize. So if you were in a rest frame that was zooming in the direction of Earth from that supernova, your time would be distorted and your space would be distorted. And when you ask this traveler on a spaceship, which happened first, he'd say, no, the Einstein got it first. And then later the supernova explodes. There's nothing physical between the two of them, but it was a very good guess. And if I had chosen a different example, you'd have been right. The star that caused the supernova that was seen in 1054 AD, which is the source of pulsars that I'm going to talk about later, that really did explode before Einstein got his Nobel Prize. Again, the order of time is inseparable from causality. If you can cause it by moving light back and forth or any other means, light being the fastest way to go, it's going to get there first, then you know what happened first. So there's a Crab Nebula, as it was when I was a boy, here as a student, and that's what we see now if you look at it, the big furry mess. And this is what it looks like. It was satellites that have since been launched and looked in the X-rays. There's a little star in here, a spinning pulsar, which is shooting out electrons, and that spinning star has the mass of the sun, it's about 10 miles in diameter, and it's distorting space and time, as we're going to see at the very end.
So if something like a supernova were to happen, just given this specific scenario, the light reached Earth on February 24th, 1987, right?
Right.
So we know how long the light took to get to Earth at that time. And so we know that date on Earth, that day on Earth happened after the supernova because the light directly affected Earth at that time. And we could use the theory of relativity to calculate the speed of time between Albert Einstein receiving his Nobel Prize and that date on Earth.
Uh-huh.
So could we use that calculation along with the calculation of the time?
Pardon this interruption, but at this point we have two groups of students who will be attending an in-house field trip. If you will dismiss them, please.
Yeah.
One
You're
group
already
will
in
be
your
joining
in-house field
Jim.
trip. We'll turn
So we could calculate the actual, like, we could calculate the difference in times between like that time and the time it took for the light to get from the supernova to Earth, and could we actually mathematically prove that one or the other happened first?
Well, that's a very good question. You could not do it because you could do it in your reference frame. You could say, oh, we're standing still on Earth, and therefore that's what it is. But let's assume, but we also know that we're going around our galaxy at a very high speed, and we know that our galaxy is going around a cluster of galaxies at an even higher speed, and we know the whole mess is going to a spot in the constellation of Hercules at an even greater speed. So you have to question, in what reference frame are you computing it? If you chose a reference frame that was not referenced to Earth, like you're saying to do, you could come up with the opposite one, and you could have the other one come first. By using those equations I showed you earlier with the little square root of 1 minus b squared over c squared.
Okay.
You have to become a freshman to be able to do it, and then maybe next year or the year after.
Year after.
However, the actual time the light reached us did come after that. It came 60 years after, we know it. I mean, because light could have, but that's the time the light hit the Earth. So let's bring the twin paradox out, which is another example of this. So you want to have a twin, are here on Earth, you're same age. Your twin takes a long trip at near light speed. So that when the twin comes back, you're each in a frame where you think you stood still and your sibling did all the action. So you each expect the other to be younger than you. The one in the spaceship says, yeah, because this guy shot away and back on the Earth, and the one on the Earth says, no, because she did that. So when you meet, who's going to be younger? That's going to be an incontrovertible event. Which is going to be younger? It's a paradox. You know the answer?
The traveled one.
If you watch Star Trek, you know the answer. The traveling one, right. The traveling one is. Okay, all right. So does this contradict it now? I said all observers are equal, and now we're saying no. The one on Earth is right. The one on Webster Groves is right. Right? Well, here's an example of it again. Maybe I don't have to repeat it. Here's the two people, and that's me, and that's my sister. Off she goes. I'm getting older. She's off, we don't know what she's doing. She's red-shifted because she's moving away. She comes back blue-shifted, moving back. I got beards and I'm an old man and she's just as pretty and young as ever. So, obviously in the pictures it happens too. Here's the explanation for it. There are 3 reference frames, not 2. One is the twin on the Earth. The twin thinks the sibling went off and then came back. The other is a frame of the twin moving away from the Earth. In that frame, the Earth's twin was always moving away at one speed, but the twin herself was at first stationary, and then when she changed direction to come back, she did double the speed to catch up. And then there's a 3rd reference frame, that of the twin moving towards the Earth, the twin coming back. She thinks that I was always going backwards in space, and that she went off at double speed, and then she stopped, and then she stopped. And then I come up and hit her again. And I come up and caught up with her. So there are 3 different ways of looking at it. It's not the speed, the time tied to the person, or the observer, that's called the proper time. It's the time of a reference frame, which is a set of x, y, and z's in time that people can set up. So at any one reference frame, you get the same answer. There are many apparent paradoxes in relativity that, like the twin paradox, that if you think about it first presented to you, you say, oh gosh, relativity's got to be wrong, you can't even explain it. And then they all can be worked out. So there, the freshman does the math consistently in any of the reference frames, the traveler's always younger. So that's relativity. I'll have a brief review of it later. Einstein went out to questioning gravity. These were some questions that actually Newton got posed with, and he sort of blew them away. But how can the Earth pull on an apple? What does gravity mean that the Earth is pulling? It's action at a distance. And so how can there's nothing touching the apple's up here, and the moon's even further. How could it do it? And the answer was that Einstein came up with a general theory of relativity. It took him another 10 years. He made many mistakes along the way, publishing things that weren't true, but finally he got it right. And he came up with this: if you have a person in an elevator, he can't distinguish between the elevator suddenly starting to move up, which is an acceleration, or the Earth's gravity pulling down. If you're just inside the elevator and can't look outside, you don't know if the force you feel is because you're being yanked up or because the Earth is pulling you down. So he took this fact, which we all know and don't even think about, and turned it into a principle. And he decided, and there it is again, observer cannot by local measurements, that's local means confined to a small area, not by looking outside the window, can distinguish between an acceleration and a gravitational field. So let's see how that fits in then. In Einstein's 1905 theory, the special theory, there's 4 dimensions, space and time. They're perceived differently by people moving at different velocities, so as to have the speed of light be constant. But space-time, the combination, is flat. Flat has a specific meaning that Euclidean geometry, which is what you've learned, applies. In particular, the sum of the angles of the triangle always come to 180 degrees. And things always move in straight lines in the theory of relativity unless they're hit by a force, and he does not include gravity. To do gravity, he got the idea that space is really curved. We're not aware of it, but it isn't flat. It doesn't follow Euclid's laws. All the stuff you learned in geometry are wrong to a very tiny extent as far as the real world goes on Earth. So just like plane geometry does not work on a sphere. You see a sphere here. There's going to be a lot of analogies between curvature, a 4-dimensional curvature, and a 2-dimensional curvature in a 3-dimensional space. So imagine a sphere, on a sphere there, and you had, say, things move in the straightest way they can on the sphere, on the balloon, which is a curved space. And you have a 2-dimensional creature doing it. The motion is seen as curved, and that's gravity. So let's imagine a 2-dimensional ant on the balloon. she might think she's walking in a straight line, that she walks the shortest way she can, but you're looking and you see that she's really going in a circle. She's really going in a circle, and it actually looks like it might even be an orbit around the top of the balloon. So the ant will say gravity brought her back. She's going in orbit here, but no, you and Einstein say no, her space was curved. She was just going the straightest possible way she could in that space. So think about that. Is that any questions about it, or is that obvious? This is a pause. Make sure you're all with me. You're all with me.
Hey,
Great.
wait, so then why are orbits elliptical in this, with this design?
Oh. So the better way to state that, orbits don't have to be elliptical, by the way. They happen to be according to Newton's laws, the orbits can have many shapes. For a very specific level of energy, they're perfect circles. If they have a bit more energy, they go in an ellipse. If they have even more energy, they go in a hyperbola or a parabola. So a lot of comets go in parabolic orbits. They don't go in elliptical orbits. So that all works out following Newton's laws, for which these laws that I've given can be simplified to the case of weak gravity.
Okay, and like an object is not necessarily following directly on that perfect sphere. It's kind of, okay.
And then how much energy the ant's got. Yes?
Does gravity affect something? Like, does it take gravity time to pull in that object at the speed of light? Is that like, say you have a black hole that's like 100,000 times the mass of the sun. I know there are ones that are larger. Let's say,
a billion.
all right, yeah, billions. Let's say that black hole suddenly appears 1 light year away from you. Will you instantly be being pulled towards that black hole, or will it take 1 light year for you
Interestingly
to?
enough, we haven't measured this. We haven't measured it with black holes. The question is, does gravity, with not gravity, but the curvature, does it move? How quickly does it move, or does it instantly happen everywhere? Well, the special theory of relativity says nothing happens instantly. Even the curvature can't go faster than the speed of light. And the way we've observed it is not by black holes suddenly appearing near the Earth, but with Jupiter. We've observed Jupiter going around the Earth, and we've seen how its gravity deflects starlight, not stars, but radio stars and quasars coming into Jupiter. And do those distortions follow where Jupiter is, or how Jupiter is moving up with the speed of light going in with its distortions of the field? And the answer is, to a part of about 1 in 1,000, we can prove that that the gravity is also moving at the speed of light. And this very important point ends up to talking about gravity waves, which is at the end of my talk. So, there he is, the general theory of relativity. In all its glory, geometry is 4 dimensions, at least, as you may know. Some of the modern theories, like a string theory, wants 27 dimensions, and sometimes it wants more or less, depending on who you talk to. And they're all there, but we don't see them because they're curved with very short radius of curvature, and we're not aware of them, but the laws of physics are. And Einstein said the curvature of space-time can be given by a matrix, a bunch of numbers, that he wrote as G. And given in that curvature, things move in the straightest possible line, which is called the principle of least action, also called the law of cosmic laziness. You can take Newton's laws and also write them in terms of a principle of least action. That's something you might do. I did when I was a graduate student. And then he had massive bodies, curved space-time. And he used the simplest formula that could approximate Newton's laws to make that happen. And in the solar system, gravity is weak. Newton's laws are almost true. But he still came out with clocks slowing down in the gravitational field and light bending as it passes through. And these were some of the first tests of the theory of relativity. They went to the Pleiades, which is a constellation, not a constellation, it's a cluster of stars. In some beliefs, it is a constellation, the Seven Sisters. And an eclipse happened when the sun was right there. In the eclipse, the sun went away so you could see past it. And we looked at the positions of the stars, and we saw that they were distorted by the gravity of the eclipse. And that was the crowning proof of the theory of relativity. I think that was in 1918. Or so, when they saw that Newton's theory also could give a prediction of it, but Einstein predicted twice as much. And we saw twice as much of a bend doing it. Newton's, of course, saying the particles being little particles, they would be bent by that too. And if you have strong gravity, you get all kinds of things that I'm going to get to at the end as well, the more exciting things maybe. So if you visit Washington, there's a statue. They got 3 of his most important equations on there. This is one of them. I'm obviously not going to talk about it. But this one is a curvature, we'll talk about it a little bit. This is a curvature of space. This is mass. So he says if you have a certain kind of mass, it will cause this much curvature of space. And that's the basis of the theory of relativity. Since then, a lot of people say, well, maybe we add another term right here. And if we add another term, you can add the certain terms, and black holes will no longer exist. Or you get other terms and do other things. And we don't know, like nobody gave it. Nobody went up to a mountaintop and said, these are it. Einstein just came up with the simplest theory. People have looked for these other terms, and they're able to set limits on them. If there is another term there, it's got to be less than a certain amount. And typically, Einstein's good to 1 part in 1,000, 1 part in 10,000 in all of these tests. Now, here's something that I'm 90% sure is right. I talked to a guy who really is an expert on the theory of relativity Tuesday. I said, is this right? I'm going to tell it to all the kids. And to give a simple explanation of why the apple falls. And he said, yeah, I think you're right. And that I should publish it in a journal, pedagogical journal. But I don't know about that. Let's just ask the question, so why does an apple fall? I have an apple right here. And so if I'm holding it up here, you know if I let go, it's going to fall down, just like the thing that did Newton. But now I'm telling you, there is no gravity. The Earth sucks. Actually, it doesn't suck. The Earth sucks in curved space. So here's the apple following the principle of least action. And there's the Earth below it. Assume, why does it fall? You'd think it's less action to stay where it is. Let's generalize one step before I talk about this picture. When the apple does fall, it's going to hit the Earth and it's going to splat, right? But the apple doesn't know that up here. It just knows the forces and whatever it's doing. So assume there was a hole in the Earth, a hole all the way through. The apple would go through the Earth to the other side and come back up again like that in a periodic motion. And that's given by straight Newtonian theory. It's actually an orbit. It's a special kind of orbit that does that. Instead of going around, it just goes up and down. And I've shown that here. The 1 here is the number of Earth's radii. Here's the apple. Here's a 1 Earth radius. It's on top of the Earth. It's over there in England. And here's -1. It's at the other end from England, somewhere in the Pacific Ocean, in the southern Pacific Ocean. If the apple were not to fall, and then this is time on this axis, the apple would just follow this red line. If the apple does fall, it goes through here, it goes through the hole, comes down to the bottom, goes back up, goes on the bottom, goes back up, and would do that forever until the hole got filled in and it did splat. So here's the apple being lazy. He sees this big warp in time. Why doesn't the apple say, hey, I don't want to go down there. I'm going to stay up here and sit pretty. I've told you there's no gravity. I've told you space is curved. Why would the apple be so stupid as to fall down a hole? None of us would, right? So, anyone want to take a crack at it?
Well,
Yes.
is it because if it's a hole in space-time, then there's more space-time out here, and forcing it down this way?
You've got a piece of it. You've got a good piece of it there. Take another try.
Is it because there's like no space-time underneath it to keep it?
Oh, no, there's plenty. There is space-time. There's still space and time. There's a hole down there. You could mark it. One could go through with a yardstick and measure each thing, and one could line it with clocks. They'd all tick. No, go ahead.
Is it like with gases where they go from high to low concentration?
I have not talked about that. And what you're talking about is time's arrow, which is one thing I left out of all these things, is like maybe time is just things going from high to low concentration, more and more random. It's another good guess, but I'll tell you the reason. It's because the apple really is lazy. It doesn't want to move a lot in space-time, not in space. If it did want to move a lot in space, it would sit right down here. But remember I snuck in that one thing about time going slower if you're in a gravitational field? Well, down here at the center of the Earth, gravity is stronger. Gravity gets, if you go down, you're in the middle of the gravitational field, so time would go slower. So going through space, it might be more work to go up and down. But going through time, it's less work because time goes slower. So if there was a clock on the apple, any kind of clock, even the way in which it rotted, if there were some germs in there, the clock would be ticking a little bit less, a little slower. It would have lost time by the time it came back up again. So it really is being lazy. It's going through a shorter interval of space and time by going down and up because there's less time and there's more space, but the speed of light, which as you know is a huge number, enters into it. So these are some words that say the same thing. And I'll go through it again, and then if anybody cares, you've got the view graphs, you can look at them. Remembering there's a 10% chance this explanation is too simple and wrong. So the red line is plot, shows the apple sitting on the tree or by the tree now, stationary in space, but it's still moving through time. The blue line is the apple free from the tree, assuming it's not stopped from the surface, it goes through the center, comes on back, repeating forever. Some kind of orbit. Number 2, I've shrunk that over to make more space. All physical objects go from one event in space-time to another, following the principle of least action. They take the shortest path in space and time. It experiences the flow of time at a rate given by its height. Time runs slower when the apple is closer to the center because of the gravitational field. And in fact, we know this and we measure it with atomic clocks. Near the sea level up here, if you go by 1 meter, it'll change the rate, the flow of time by a part in 10 to the 16. And we can measure this with our clocks, which are that accurate. It's actually a problem now. If you want to make clocks that are 100 times more accurate, because we have atoms moving up and down in the clock, and what exactly time are they experiencing inside the Earth's field? So there's the part 3. Distance depends on both separation in space and the speed of light from the separation in time. That's a big number. It moves through time, not on the tree. If it's only on the tree, okay, assuming it hadn't moved on the tree, we have it not moving through space, but it is moving through time, and you get this number. The falling apple moves through space and time in order to move slower through time. So you get those things. So when you get to the geodesic distance is what we call it, it's less going up and down. Have I beat that one to death? Beat some of you to death?
Does that mean time has a lot of energy?
Time has a what?
Does time has energy? Because the apple is lazy, so he wants to travel less, like in time. So the apple actually travels in the space.
It travels in space and time.
Yeah, but he traveled less in time.
Yes, it's exactly what it means. We'll travel less in time.
So
If you have the clock up here, if you have 2 apples, you have a twin apple and a regular apple, each with a little clock in them, this will say 1 time when it comes back. When this one comes up, its time will be a little less.
Okay, so does that mean like time is a stronger force?
Well, and these,
So if something
well, we got the speed of light right here, and that's a big number. So it's not a force, but definitely. And time is in terms of explaining all this, time is the dominant one. It's clobbering space. But of course, that's because we're human. And we think of the Earth's distance as a long way. But if we were some super big giants, let's say a combination of some life form that was really made out of galaxies, then this would be some teeny, teeny little space.
So stuff ages
stuff goes slower in time when it goes faster in space, and when stuff goes slower in space, it goes faster in time. Is that
Well, in a gravitational field,
in a gravitational?
well, it depends now. Because you could have the apple stuck to the tree so it doesn't move at all. And then it's not going anywhere in space, it's only going through time. But if you're following a geodesic, you get this sort of situation. Yes?
So, if there's no gravitational field, does nothing age?
No, everything ages. The apple will still age. Gravity doesn't make us age. But the aging will be different. Different observers will say different things about the aging. And if you really don't want to age, you ought to go down in here. In fact, there was a recent science fiction movie that really clobbered that idea to death.
I don't really agree with that.
Well, science fiction will take liberties. There's no question about it. But that's part of the fun of it.
Taking kind of a throwback to when you were very early on talking about how Einstein was thinking about light and how you would perceive it if you were moving at the same speed as it, and then you said like you can't do that or anything, but how does light experience time? If it
Well, light doesn't experience time in some way. Photons do not age, but so they're always the same. They could be. We're seeing now light that was emitted from shortly after the Big Bang.
well, but then how does it exist if it's intrinsically the definition of light is a changing magnetic and electric field? But it doesn't experience time at all, then how on earth does it change?
So if light itself doesn't experience time, but we who look at it experience time. So the question is from the point of view of the light, why is it there? Well, because you may know light has a duality. It has photons, it can be a particle, and it can be a wave. But to ask the question, point of view of the light, is a trick question in the point of view of relativity because no observer can go at the speed of light. So you can that's one way to weasel out of that. But those are the kind of things that people question relativity with even now. And actual light is not that, of course, because no light travels at the speed of light. In this room, the light is held down by the air. It goes a little bit slower. In outer space, there's no air, but there are electrons, and they slow down light as well. So true light, traveling at the actual speed of light, don't exist. And you can also get coordinate systems now because the whole range in curved space where light seems to travel faster than light. But that's due to curved space.
So you said that like no light can travel at the true speed of light. So how do we know the exact speed of light if no light can travel at?
So, well, how do we measure the speed of light? That's a question that can stump a lot of people. The accuracy, the rate at which light slows down is very small. The slowing down in our atmosphere is very small, so we get a number. And the first measurement of speed of light was by Romer, who was the satellites of Jupiter, seeing the times of eclipses. And when Jupiter was further away, they came up at one time. When Jupiter was closer at another time, they were going through space. There was no air to slow it down. In a typical experiment, depending on how you're doing it, if you know there's an effect is distorting things, you try it with double the effect, triple the effect, 4 times the effect, and then you extrapolate down to not the effect at all. So you can get with not only the speed of light, but almost any other experiment you think of is done that way. Yes?
So if light doesn't truly travel at the speed of light, does it experience time?
Does the light experience time?
If it's not moving at the actual speed of light, it has to experience some speed.
So then if
Yeah.
my next question would be, would it decay eventually?
People have looked for light decay, and they haven't found it. They've looked for light over long distances. And one of the theories to explain the redshifts of expanding universe, if you look at galaxies, the further away they are, the more their light is shifted to the red, which we interpret to mean the faster they're moving, they say, well, it's not that they're moving faster away, it's that the light gets tired as it comes in. But arguments against that can be raised on the fact that all different colors of light come at the same redshift. So it's the different wavelengths of light do not get tired. So the question is, if light goes in its own reference frame, will it age? Well, no aging has been known to happen to it. Best question I've had today. Now go back and think about it. Well, we'll go on then, see what other great questions I get. All right, so here are some consequences of relativity. Relativistic timescales. We now have to have many different kinds of time when we talk to each other. So like time on Mars, time on the Earth, time at different places. It affects GPS satellites. Rather than go through this list, I'll just hop into the list and see how far I get. See if that went. GPS clocks and relativity. If we had the corrections for relatively wrong, GPS would not work. So we know we've corrected it right. The satellites move at about 3 kilometers per second. Time dilation slows them down by a part in 10 to the 11th. But the Earth's gravity slows down spacecraft less when they're up there than down here. So weaker gravity makes them faster by a part in 10 to the 10. Gravity wins. The clocks in GPS run faster than on the ground. And when people first launched GPS, a lot of people thought that, say that the engineers didn't believe this. They didn't believe this theory of relativity. So they designed them with enough freedom that if relativity was wrong and everything went at the same speed, they could adjust for it in the satellites. But no, relativity was right. Now here's gravity waves. I have an example here of a pulsar, pulsar is one star rotating. These are two stars in orbit around each other. They're distorting gravity. That makes waves. And you can see the waves coming in. These are distortions of space and time. So if you're standing on the Earth here with a telescope, you will see your time distorted and your space distorted in different ways. And if you're comparing different stars that have a time on them, different pulsars that rotate when we get their apparent rotation time by the rate of their blips, we should see the effect of these waves. There are people that are looking for those waves now. They have upper limits. There are also people building systems on the Earth. Oh,
how does dark matter affect light going through it?
Dark matter, I haven't talked about dark matter. Dark matter does not interact with light at all.
Okay.
So the light just goes right by.
Well, I thought that's how we knew it existed, how like light went through it.
We know it exists from its like effect.
Yeah, like
the gravity of dark matter.
That's what it was, not light.
Gravity. The dark matter will make these ripples, and the gravity of it. Good. So, sorry, it doesn't interact electromagnetically with light. It still acts with gravity. Yes, so you got the right answer there. And there was a recent time where we actually showed an interesting fact that's just come out, where we saw the gravity of dark matter distorting the light, and we inferred there was a planet going around a star. Because of we saw a blip as the one star got magnified by the gravity, and then a smaller one as the planet did. And now we have actually imaged the planet to show that there really is a planet there. We've seen it. So it showed that in fact, dark matter was through its gravity, and there were some multidimensional brains, and they collided, and that collision created the Big Bang and time. But you'll notice if that happened, time is sort of involved in all that as well. What do you mean to say they collided? And when did time stop? Maybe time will never stop. That's how we tend to think of it as we go through life. But others say, no, it will stop when the universe collapses upon itself. That's possible. Or it could stop right now. Or just in a second from now. Or when the brains separate, which will rip the fabric of space and time, that could be going on right now. We wouldn't know it until the rip comes to us. And all of these things can be the subjects of books and conferences and arguments. I'm just telling them now to get them out of the way and set the stage for how we got to where these questions could even be considered. And this is one that I really like. I don't like it, but it really intrigued me. Maybe it'll slowly die out. The current theory says the universe will expand indefinitely, in fact faster and faster. Will be left after many, many eons, will just be a dilute gas. That's all it'll be. And there'll be little fluctuations back and forth, but there'll be no way to make a clock in such a thing. No way to keep track of time. So what does it mean to say there's a time? There's just this little gas that's going back and forth. Or maybe it's a trick question because time doesn't even exist. And there are ways that you can say that. Or some people say that it made a magnetic field. So changing electric fields and magnetic fields, they can switch back and forth and make a wave that will move forward. And he could do the math, and he came up with a startling fact. The speed of light he got by doing the math through that is correctly predicted by what we know from having measured the speed of light. This is the famous Maxwell's equations. Now I'm going to show them to you. There they are. And these say in mathematical form just this. So, and that was of course one third of religion, that God just set up all these equations and then everything else followed. So we're not talking about religion here, we're talking about everything that we don't know. Like the Michelson-Morley experiment came along in 1887. These guys decided, well, if it's a wave, what's it a wave in? It's got to be a wave in something called the ether. So light was believed to be a wave in the ether, and if it's a wave in the ether, then its travel time would depend on how the Earth was moving. So if the Earth was moving with respect to the ether, it would see light as moving slower if it was moving in the direction of it, or it would see light as moving faster. So these guys, Michelson and Morley, tried to figure out how light was moving in absolute space, which Newton also believed in, by setting up this little apparatus. Final completion of Einstein's theory of relativity this November. So there's the beginning part. Here's some practical definitions of time. I was, for my position at the Naval Observatory, once you get this job, they say, you know everything. I got called and asked to say what the time was, and I gave this definition. That coordinate, which can be most simply related to the evolution of closed systems. You can still find it in Britannica online. So this is a practical definition. It's a coordinate that helps you explain what's happening. That's sort of like defining a symphony by the notes in it. It's missing something. And a lot of people think, well, go over some more definitions. I don't think Yogi Berra really did this, but it's been ascribed to him. Time is nature's way of making sure everything doesn't happen at once. And space analogy. This actually has validity to it. And so one of the questions that people have is, when did time start? You think we know what time is. Did it just start now? Maybe, we just began now, and everything from dinosaur bones to bad grades, it's just memory that we were created with. That could be. A lot of people say maybe it started at the Big Bang. That's a singularity. I'm not going to talk about it, but I'm sure you all have heard of the Big Bang. Or maybe it went infinitely in the past, and the Big Bang was just an event. And some people say, well, in the past, time runs backwards. It's a human construct that time goes forward. That's not a question. Not a question. Okay. But let's start with Newton's mechanics, which is how people really tend to look upon it. And he thought that time flowed evenly throughout the universe. And he came up with other rules, like energy and momentum are conserved, and F equals ma. And he sort of set the stage for what we call classical physics. And I would call him the most brilliant scientist I know of, although everything he said is no longer believed. Or I turn that around. Nothing he said is believed anymore, to be exactly right. And we're going to talk about his theory of time there. And I'll give you something about his law of gravity first. It was indeed inspired when he was sitting underneath a tree trying to escape the plague of London, and he saw an apple fall down. And the mass attracts mass. Heavier bodies pull more. Heavier objects feel more force, but they have more inertia, So heavy and light objects fall at the same time. This contradicted Aristotle, who thought heavy objects fell faster. And he also came up with gravity weakening at the square of the distance. And that was an important thing, and he developed calculus to show that the force that pulled on an apple, if it fell with the square of the distance, would describe the moon in its orbit. That was not a simple thing, because with the moon far away, you could think of the Earth as a little point source and the moon going around. But the apple, right next to the Earth, you can't no longer consider the Earth as a point source, so why would that work out? He showed with calculus that it all works out. And what did he think light was? Well, he thought of little particles, they could spin, and they didn't have to be round, and they had all kinds of things, and they had mass, like particles, and when they hit your eye, you could see. Your eye would detect them up. And he had theories that red light was heavier than blue light, and it traveled with glass. And this was widely believed at the time. They thought it was great. Although one of his contemporaries, Robert Hooke, you might know of Hooke's law of how springs work, he said, nah, light's a wave, but he wasn't believed. He wasn't as smart as Newton after all. And so this dominated for 2 centuries. Alexander Pope, an Elizabethan poet, said, nature and Newton's laws lay hid in the night. God said, let Newton be, and all was light. But science progressed. And in 1861, Maxwell showed that light was waves. And here's his reasoning, which I think you all know the pieces of. You may not have put it together. Changing electric fields make magnetic fields. You all learned that in grade school. That's how electromagnets work. And then he thought changing magnetic fields make electric fields. That's how generators in the car work. Change electric fields, you make